again, so I'm a principal research manager and a project lead at Microsoft Research AI for Science. I'm based in Cambridge, so very glad to be here and seeing everybody. So yeah, so I think if you come here last year, I think one of my teammates, Daniel, may give a talk about some aspects of the talk, so you may not be surprised by some of this, but hopefully I'll give you something new today. So yeah, so today I'm going to talk about some of our works that we have been doing at our team around building some foundational AI models to accelerate material discovery. So as many of you who have know, right, so materials design is really one of the cornerstones of modern technology, and many of the problems our society facing today, they are really bottlenecked, right, by the good material. For example, if you can find better batteries, your electric cars can run much longer. And many people believe that if we can find a material that can absorb and recycle soft carbon from atmosphere, then we can create an industry that was able to do carbon capture, then this will be a key component of reaching carbon zero in 2050. So many of this, right, is bottlenecked really by finding a good material. So the problem of finding a material is really often about finding a needle in a haystack, because you're looking for a material with a very special property that you normally don't find, right, in the average material. So this is an example of something called LGPS. It's a material that was discovered inside Toyota in 2011. What's special about this material is that it is a solid material, but the lithium ion can move inside this material as fast as the liquid. As a result, most battery manufacturers today, they're racing to having this material to be deployed in the next generation battery technology, next generation all solid state battery, which will be much safer and much longer. So as you can see, right, so our humans' ability to be able to find this type of special material is really bottlenecking many of the problems, right, so that our society is trying to solve. And so the question is that can we develop AI models that are able to accelerate the discovery of such extraordinary materials? So in our view, right, so we believe that there's two major opportunities that AI brings, right, in accelerated material discovery. The first is coming what we call AI emulator. What it means is that traditionally, right, what people have been doing is that people kind of are doing material discovery by running a lot of these calculations using quantum mechanics. But what you can do is that you can actually train a machine learning model that can do these simulations 3 to 5 orders of magnitude faster, right? So this allows you to compute the property materials much faster and screen those property materials much more efficiently. So the second opportunity, what we call, is something called AI generator, which accelerates the exploration of the novel materials so that in a more efficient fashion. Because traditionally, people just do this in a more brute force fashion, but now with generative AI, you can actually explore the material space much more efficiently by using the materials property that you're looking for to guiding the exploration. And what is more significant is that you can actually compounding these two types of foundational capabilities. You can have a generative model that proposes materials and being evaluated by an AI emulator, and so on and so forth. So therefore, this kind of feedback loop really allows you to much more efficiently explore the novel materials, basically across periodic tables. So what we've been doing at our team is really about building up some of these foundation models along these two aspects and hoping that this can be used for a broader set of material design problems. So I go into each one of these models, but since this is a very broad audience, I'll introduce a concept just to maybe a short course, right, on a bit of physics before you go into details. So what is the concept I want to introduce today is something called a potential energy surface. It's a very important concept that describes a lot of the properties that materials material scientists cares about. So if you imagine the structure of a material, right? So they usually describe a bunch of atoms inside a periodic box. So you describe them based on the type of atoms, its positions, and a periodic lattice that defines the periodicity. So once you know this material, right, you can imagine that you can define an energy function that basically describes what is the energy of a specific structure of a material. You could imagine that this becoming a bit like a potential energy surface, because if you slightly perturb an atom, right, inside of this material, you would imagine this energy will kind of increase because you're kind of moving the atom away, right, from its kind of equilibrium state. And so basically this is, so therefore this is a kind of a continuous function, right, across all the possible positions that an atom have. And you can define this function for any material if you plug in different type of atoms in it. So this is like a universal function that in principle is actually very well defined. So the good thing is that you can actually compute compute the energy and the gradient of this potential energy surface at every single point by solving the Schrödinger's equation. So this is quite expensive, but if you have a lot of compute, you can actually do that. So this creates a way that you can generate almost infinite data to learn this potential energy surface. And the second good thing is that once you know the potential energy surface, one could actually derive all kinds of materials properties, including mechanical, thermodynamics, and transport properties. Because what basically this property is about is basically about how each atoms move, right, inside these materials. So this kind of motivated us to lead to this work, which we call MatterSim. So this is the first AI emulator that really tries to learn the potential energy surface across the periodic table. So we're taking all the materials we know, right? We kind of try to learn this potential energy surface around it across a very broad range of temperature and pressure, covering all the temperature pressure that human will have access to. And we use all this data to learn a big neural network. And this approximates the potential energy surface. And once we learn it, you can show that you can use this model to do many, many things. Let's say you can compute the thermal transport behavior. You can compute the phase diagrams, which basically describes at which temperature the material will melt, etc. You can compute things like how fast the lithium ion move inside this material. So this is becoming a bit like a foundational model. Some people would call this in the field. So we have open source this model on this website, and you should feel free to play with it. So let me go into a bit of details over how did we kind of build up this model. So a key component of the model creation is really about sampling the potential energy surface with a lot of quantum mechanical calculations. So we use something called, we use active learning to guide the exploration of the space. We actually use uncertainty to guide the exploration. What we do is that we start with a few of seed materials, and we sampled points around it, and then we train a predictor which have uncertainty estimation components in it. And then, so therefore, for all these candidates, we only run DFT on those areas which have very high uncertainty. So therefore, you you only sample those uncertain points while you are running these large-scale DFT calculations. And this is iterated over 5 to 6 times. And until we got a very, very big data set. So what it leads into is this data set that incorporates around 17 million structure energies and a lot more forces. So you can see that this is the plot of all the data points in the effective energy and the stress, which corresponding to pressure space. You can see that it covers a much bigger space compared with the previously very well-known data set that is something called MPF 2021. And the one key aspect of this data is that it's also highly uncorrelated, which means that every single data point, because we use this uncertainty quantifier, they are highly correlated. So therefore, it's actually, there are some bigger data sets out there in the community, but this data set is actually one of the most diverse compared with the one that is already available on the public domains. So we also developed a transformer-based architecture to really fully consume these data sets. So I wouldn't go into too much details, but the core idea is that you basically use the pairwise periodic distance as the key features for the attention weights in this transformer. And we use some kind of equivariant output so that we can have the force and the stress predictions, which are basically vectors on each node, to be equivariant with respect to the rotation of input atoms. So once we learn this model with a lot of data and a very big model, so we can actually show that this model have significant improvement over existing models, including models like say Maze from University of Cambridge or Genome, which is from Google DeepMind. And then, as just to highlight with one example, right, you can then immediately do a lot of these things, zero shot with the model, like predicting at which temperature pressure a specific phase will melt, go to a different phase, and this will have a very good correlation, with consistency with respect to experiments. So one actually very quite significant thing people have been facing in the community is the stability of running molecular dynamics. As you can see in this plot, right? So this is when you actually try to run molecular dynamics, very often a lot of the force fields people see, if you run a long enough simulation, it will explode. So this is actually coming from one of the papers that we worked on before, where basically we show that when you're evaluating this kind of force field models, only looking at the force is not enough. You actually have to look at those, for example, stability of running simulations, etc., because those are the things that really matters for the real world domains. What we observe is that because in our model, right, we actually sampled a lot of these high energy states, this actually significantly improved the stability of these MD simulations across a broad range of different type of materials. Here I give you a bit of a success rate of stability, and this is the quite much improvement compared with all the other force field people have seen before, because the fact that we are able to sample this very high temperature and pressure regimes that normally previous force fields are not trained on. Finally, let me give you an example where also, like, just to give you a note that there are also limitations of this base model, because this is using a certain level of quantum mechanical theory called a PBE functional, which have certain limitations. For example, it wouldn't fully describe the water, which is actually quite complicated if you're thinking from a quantum mechanics point of view. So therefore, there are some inconsistencies with respect to the worker. But what you can actually do is that you can use a quite a small number of high quality kind of quantum mechanical calculations to basically augment, to fine tune the base model. So this will give you, because the base model already have so much knowledge about this domain, you can have a 30-fold data reduction in order to fine tune this new domain, so that you can actually simulate water very efficiently and get the so-called RDF curves very consistent with respect to experiments. So now I give you a bit of an overview about our model, right, MatterSim. So now let me give you an example about how you can actually use these type models to really do some material discovery. So this is the work from our colleague from Azure Quantum team, where they use a very much MatterSim-like model, where they try to screen 33 million candidates for materials and trying to find some novel solid-state battery for solid-state materials, solid-state electrolyte for the lithium-ion batteries. You can see that because of the acceleration coming from these AI models, you can do this screening in 1,500 times faster than what you could normally do and then you can do this entire work in around 1 week on the Azure cloud. And so the team actually managed to work with the Pacific Northwest Lab in the United States, where they end up synthesizing a real material in the lab. And as a demonstration, they even made a clock coming from the battery that was designed by the team. So again, I want to note that this is not any kind of a revolutionary battery material. So this is more like a proof of concept, showing that you can go close the loop, really finding the real material. One thing that this entire community is now trying to go towards is really showing AI can design some real breakthrough materials that have broad impact, right, in the industry. This is something we're all working towards. Okay, so then now let me move on to the second part of the talk, where I'm going to talk about AI generators. So as you can see, right, in the previous example, if you only have an AI emulator, in order to find some materials, you actually need to screen through tens of millions of materials, which is quite inefficient, right, if you think about that. So therefore, what this really brings is that you can actually do this exploration in a much more clever way. Instead of just screening a lot of random materials, you can then use the property that you're looking for to really guide the exploration of novel materials. So this is MatterGen is the first model that we have been able to show that you can actually have a generative model that enable broad property-guided materials design, generating materials given both specific chemistry, specific electronic properties like band gap, specific mechanical properties like bulk modulus, or specific magnetic properties. Let's see the magnetic density. And this is the first time we were able to do that. And this is also why this paper is recently published on Nature, and we have open sourced the model as well on the GitHub here. So the core of the MatterGen is a diffusion model that is specifically designed for materials. As I've described later, right, materials, you can describe this as a bunch of atoms and its positions as well as periodic ladders. So we build up a specific diffusion process for this type of materials. So therefore, during the training, right, you take stable materials and you corrupt it, both the atom type position and the ladders. This gives you some random material, a random distribution, from which you can sample from. And then in this process, you kind of learn a denoising model that can kind of denoise a noisy material into a stable material. Therefore, during the generation process, you just sample random material, and then you generate the novel material on top of it. I'm going into a little bit details because we actually spend quite a lot of time designing this diffusion process for each component. For example, for atom types, because it is a discrete variable, we use something called D3PM, which is a discrete diffusion process, which you define some kind of a Markov transition matrix for the forward process, and we use something called the master diffusion, which means that at each step you have a certain probability of transiting into a master state, and then in the denoising process you go from master state back to a real state. And then for the coordinates, there is actually some speciality about the material because you're looking at a material in a periodic box, right? So if you move an atom from outside of this box, it will go back right from the other side because of periodicity. So in geometry, this is described something called a torus, which you can actually define a corruption process based on this torus geometry using something called rep normal distribution, which is defined by this equation here. So this allows us to define a forward diffusion process for coordinates that truly respects the periodicity of the material. Finally, it's about lattice. So the lattice is basically the periodic box, right, that I have mentioned earlier. We just use the standard VPSDE, but we actually slightly adjusted the limiting mean and the variance of this distribution, because we found that if you actually don't do any changes, this will be 0. So that at the limiting distribution, you have very skewed box, which introduces a lot of instability during the training. So therefore, by modifying this, you can actually have the limiting distribution to be a cubic box, which is much, much more stable during the training. And then combining all these innovations, right? So then we actually build a diffusion model specific for materials, which I will show later that actually is quite useful for the model performance. Another very important component, obviously, right, is about the training data. Training data is really the key for developing a lot of these foundational AI models. So in here, we collected all the known kind of stable materials that is available on the public domain, mostly from these two sources. One is Materials Project, second is Alexandria, which is the more hypothetical data sets. And we collected all this from public data, but the key thing we did is that we run quantum mechanical calculation ourselves. So at the beginning, there's maybe around 3 or 4 million of these data points, but by running calculation, we remove those unstable points. So therefore, this only leaves the stable materials, which we found that by having only stable high-quality materials is actually very helpful for the model performance. And this gives us this data set around 600,000 structures. And by kind of training the diffusion model with this data set, this leading to the base model of a MatterGen. So obviously, a key aspect, right, about this generative model is about evaluation. And it's actually usually not easy to develop a evaluation metric, especially for generative models. Here, we developed a novel metric, really spending quite a lot of time really thinking about these problems. So we believe that in general, for a generative model, you need to look at 3 things, right? What's the quality of the things you are generating? Are they diverse, right? Or are they novel, right? So therefore, these are the 3 key aspects that we evaluate. So therefore, we basically define stability and uniqueness and novelty as the 3 key aspects of measuring the quality of the generative model, and we combine this metrics called stable, unique, and novel with the interesting abbreviation SUM as the key metric for the generative model. And we evaluate this all the models that are available back then in the public, and we show that MatterGen, by doing this architecture innovation, we actually have 1.5 improvement compared with the state of art back then, called the CDVAE. And because this additional data accumulation, this gives us another 1.8 time performance, as you can see. So the improvement in model coming from both the model architecture improvement as well as the data. So this is what I mentioned for the base model, right? So when you sample from the base model, you are kind of generating a lot of materials across the periodic table that are stable, novel, and hopefully diverse. But this is not the most interesting thing, right? So the most interesting thing is really finding a material that can become a battery material, for example, right? So this is enabled by fine-tuning. We take the base model, and what you need is a small label data set where you have a pair of structure and their properties. And then you can add this property that you're looking for as a specific condition. And then we put this into MLP, and then sum the embeddings you're getting into the node embeddings of the score network. So this will kind of alter the scores of the score network. So therefore, once you're doing the fine-tuning, during the generation, you will only generate materials satisfy the properties that you are defining. And in here, we use something called a classifier-free guidance that is consistent with the same as people using text image generative models. And the good thing here is that this condition can really be anything that you care about. So therefore, material scientists, they can just bring in their own data for the things that they care about. And the second thing is that you don't need a huge data set here because it's just fine-tuning. So we have tested the smallest to 5,000 data points. Now you can actually fine-tune a model that can generate materials based on the properties that you define. So this is one example of one of those fine-tuned models. Here we are using it to discover novel materials in this specific chemical system called strontium vanadium oxygen chemical system. You can see that MatterGen generates a lot of novel materials, as you can see here. And we benchmark against some other methods in the domain called substitution on RSS. It shows that it is better than RSS. It's kind of similar to substitution, which is one of the very well-known methods people use to discover novel materials. And also the key advantage of MatterGen is actually in 5-element system, which are basically the more complex the system is, the more efficient the generative model is, because you're looking at these complex regimes where language model can provide, the generative model can provide a lot of good prior. So this is actually one of the key results we have in the paper, which is that you can show that you can have fine-tuned a model to generate the materials given required magnetic, electronic, and mechanical properties. So in here, this blue distribution are the property of the materials that we are generating, and the gray distribution are the training, kind of basically ground training data distribution. So what is significant here is that you can actually shift the property of the material you are generating to a value that is very far away, right, from the peak of the training distribution. This is significant to material scientists because it means that you can find that this material with extreme properties, let's say the super strong magnet, right, or super hard materials. And this is usually the kind of things people really cares about, and this is actually hard. And we're initially when we saw the result, it's also surprising for our team that we actually can do this so well in shifting the distribution. So this is another example, right, where this really shows the advantage of these generative models. So here the x-axis is the number of DFT calculation, how many times you calculate. The y-axis is the number of material you find. You will see that with generative model, right, as you keep increasing your budget, you're finding more and more materials that are super hard, which is above bulk modulator above 400 gigapascal. But with traditional screening-based methods, you saturate. So this is why your generative model can explore a much bigger regime, finding a lot more of these novel materials compared with what the traditional people have been doing with these screening-based approaches. So finally, I want to show something in our paper, which actually we tried a proof concept. We tried actually to synthesize one material in the lab to go all the way. So in here, this is an example where we asked the MatterGen to generate materials with bulk modulus of 200 gigapascal. We generate 8,000 materials, and basically then it kind of gradually filters down, and we send 40 into the lab, and one of the synthesis is successful, and at the end, the bulk modulus is around 169 gigapascal, which is within 20% of error with the actual conditional value. We think this is a very good initial proof of concept, showing that you can actually have a real material made in the lab. But obviously, there's a lot more work that needs to be done to really, can we actually find a real material, right, that can be deployed in the industry? So that's something we are actually moving towards. So thank you. That's actually pretty much my talk. So I wanted to kind of go back, right, to go this big picture. We are trying to build up these two foundational models. One is MatterSim, which is an AI emulator that can simulate all kinds of materials properties. Second is a MatterGen, which is an AI generator that can generate novel materials guided to the property that you're looking for. And these two can really work together as a flywheel, where you have a generative model kind of propose candidates evaluated by emulator, and together they can actually be used to explore broad range of materials. And the one thing we are really hoping to move towards is working with partners to having this material really synthesized in the lab, and hopefully when they deployed in the real world, and hopefully then we can demonstrating AI is really showing real world impact in a lot of these domains that people cares about. Finally, I would really want to thank my team. So as noted, right, by Haiping earlier, so this is really teamwork, right? So we are a very highly collaborative team with people who are kind of a domain experts as well as machine learning experts. We work super collaboratively inside our team, and we actually have a team across the world working together on these kind of problems. So all this work is really done by the team who actually spend two years on this kind of problems, really making the model work. And we're continuing building the next versions of the model, hoping to improve some of the key aspects that people cares about. So finally, I want a small advertisement. We are hiring not only my team but also the broader AI for science. We're currently in the hiring stage, so therefore, if you're looking for jobs, feel free to go here. So now, and let me go back, and thank you everybody, and happy to take any questions.
Any questions for this presentation? Yeah, please.
Hi, Tian. Thanks for a lovely talk. It's amazing what you're doing with MatterGen, and you're discovering wonderful crystals. But of course, materials are more than a crystal structure, and many materials that we deploy in the real world are a product of crystal structure and microstructure and multiple phases and so on. Do you see a route to extending these kind of techniques to those kind of more complex real-world materials?
Yeah, so this is actually really one of the frontiers, right? So going from kind of crystal structure to this kind of higher level structure, let's say the defects and etc., right? So I see this as a frontier, and there are people who are building these workflows, right? They can partially modeling the grain boundaries, modeling the defects, right? At a higher level, and there are some efforts people doing kind of a bottom up, right, from atomic level, and there are also some efforts people go a bit of like top down, where you take a lot of experimental data and train an empirical model on top of it, right? To me, it is still a bit unclear, right? So I think it's somewhere they will meet at some stage, but this is an area where I see is like the frontier of the field, and I see, yeah. So therefore, I think the way if you're looking at thing about perfect crystal, right? Fundamentally, the property of material is determined by this fundamental physics, right? So this provides a bit like a basis, while defects and etc. building kind of building on top of it. So therefore, if you can find a really really good materials using this kind of a perfect information plus more modification, I think you can go, you can achieve certain milestones. But if it will not work for all kinds of materials, because for example, for batteries, some problems in the interface, etc. So yeah, so in short, I think these approaches we're taking based on simulation really can push a long way. And then we are also trying to kind of build, having additional layer on top of it, really ensure we can refine a material that people can really make, and then having those defects and on top of it. But again, it's a bit of like a frontier, as you have mentioned.
Fantastic. Thank you.
Yeah, thank you. I think it's about the time. If we don't have more questions, and okay, we can.
Yeah.
Is this? Oh, firstly, thank you so much for your talk. And then I had a question in terms of like bridging the gap between like generation of candidates and then like synthesis of the actual material. So I see here that we have like an emulator and a generator. Do you see like any way in which AI can be used to like also bridge the generation and the synthesis gap? Because I understand that like synthesis is also a really tedious task and there's a lot of like risks associated with it.
Yes. So yeah, there are a lot of things you can already do from the simulation side. Right? For example, I don't know how familiar you are with this, but for example, people compute things like phonons, and people compute things like, for example, some of the workflow we have here is that we take the simulated material, we put it at a very high temperature, like a 500 Kelvin, and only for those that are stable at this very complex environment, we will try to make it, right? So there are some things one could do in the simulation domain to eliminate those unstable candidates. But again, I would say the synthesis prediction is really one of the hardest. So I was in Singapore earlier this year, where I think they actually had a really nice workshop bringing almost all the AI for materials folks around the world. And this is one key topic that people keep bringing in. And generally speaking, in the field, there's two directions you go into. As one is simulation, second is just building automated labs, and then trying to create a lot of the data, and then train the model. And I think it's a bit unclear which direction will be the dominant. Probably it's maybe a bit of both again. Yeah, but this is also a bit like a frontier in the field. But this is one of the bottlenecks because you can actually create a lot of these hypothetical materials using computation. But one of the synthesizing them is one of the key bottlenecks.
Thank you very much. It appears as though you've combined expertise both in AI and materials. For many of us in this room, we'll be working on tasks that require multiple expertise. Do you have any lessons learned, any advice you can give us on how to do that?
Yeah, that's a great question. So we actually spend a lot of time doing that, our team, because basically half of our team coming from machine learning domain and half of the team coming from material science domain, right? So when we first put the team together, people don't speak the same language. People cannot understand each other, right? So it really takes us, I think maybe around 1 year for people to fully kind of understand each other. And now we have a great team that really people speak the same language. You can understand each other. So the way I see it is that you really need to put people together. You really need people from the different kind of disciplines together. So therefore, I think workshop like this is actually such a great opportunity, right, to do that. And also, I would say it's an aspect of community building as well, because as I see the AI for materials community is similar. Like I think in 5 years ago, like people in computer science don't know anything about materials. People in material science don't know much about machine learning. But now there's a community that actively talking with each other. So I think this is also about the community building, in my view.
I think we can take one more.
Obviously, a question about manufacturability. So similar to the
Okay.
question. How do you transfer solid design to? Would it be something you include again in the process you have? So obviously, you design for certain characteristics. Do you design for manufacturability?
Yeah, it's again, like I would say, it's a hard question and very hard. We're also learning from that. So there's certain things you could do right in the simulation, and then I think also the building the lab, creating the data, especially negative data, where which material cannot be made is really the key. And I think this is an area that everybody knows is a big problem, and the people are working on that from different domains. Different
Brilliant.
aspects.
Thank you.
Yeah, well, Happing will ask the last question.
And thank you very much for your inspiring talk. I have one question. Is something that I experienced at the conference in Liverpool is as strong and as big as Microsoft, right? You have the unimaginable number of GPUs and computer power and the finance to fund research. But I understand there must be problems that you know that you will not tackle now, right? So there are unsolvable problems or some problem. How did you decide or like identify? Okay, we may not work on this problem now, right? So how did you decide like which problem to work on and which problem to tackle later?
Okay. I think that's a great question. I can say two aspects, right? One is like, in general, I would say AI for material is something that I would say like everybody know material science is something that really bottlenecking a lot of societal problems. So therefore, having AI to be useful for material is really, in general, I think we should work on, right, at Microsoft, and that's one aspect. And then deciding what exactly to work on in the near term, I think this is a great question because this, to me, I think this kind of in a way distinguishes, in my view, industrial research and academic research, because industrial research you really need to deliver in a limited domain, maybe 2 or 3 years. So therefore, we really look for these areas where A, you have a lot of data, or you can generate a lot of data, right? This, in our case, we can generate a lot of data using simulation, right? And then I would say there is an interdisciplinary component because that's kind of why we create this team, because we created this team because we want to build an interdisciplinary team because we know it's generally not easy I'm also coming from academia because I know it's not easy to create this to cross the departmental boundaries, etc., to build these interdisciplinary teams. So therefore, in short, I think the key is about data. And the second is about how to create an interdisciplinary team to do around it.
Thank you very much.
Thank you, Tian Xie, for the